welcome to Shanti-Peace for Mathematics. The goal of this video lecture is to understand what you mean by curvature and solving some examples based on curvature. So to understand the curvature, I will consider one x-axis and y-axis. Suppose you have this is your x-axis and this will be your y-axis, and you have given some curve which is in the form of f of xy equal to 0. Let's say that curve is something like this. This is the given curve, and there is a point P on this curve, and Q is the neighboring point of this point P. This is the AP, is the arc. So that is, this is S. So I am saying that AP is the arc. The length of this arc is S. Then PQ is the arc, which I can say it is delta S. And this tangent at this point P, let's say this is the tangent at point P, which makes the angle with positive x-axis xi, and the tangent at the point Q, let's say this is the tangent at the point Q, it's making the angle with positive x-axis as xi plus delta xi. Therefore, the angle between these two tangents is delta xi, and you can just say that the tangent has turned through the angle delta xi, and this turning of the tangent, it's called the total bending or total curvature. So ultimately, what you mean by curvature is the bending of the tangent, or I can say a rate of change of tangent. So the average curvature of the RPQ, that means average curvature of this RPQ, is nothing but the delta xi upon delta s. So in this length, this much of bending is there. Now when you take this limit delta s tending to 0 here, then it will define a curvature of the curve at the point P. So the curvature at point P will be limit of delta s tends to 0, delta xi upon delta s, and that is nothing but the d xi by ds. So I can say it is the rate of change of tangent with respect to the length. It's called the curvature of a given curve at the point P. So we need to make here some remarks. Let us consider the first remark. This delta xi we have measured, that is in the radian, and the unit of the curvature, that means unit of this curvature, is nothing but the radian per unit length. So the unit for this curvature is nothing but the radian per unit length. So I can say, for example, it is radian per centimeter or radian per meter. That way you can have the unit for the curvature. The second remark I want to say is the radius of curvature, the definition of the radius of curvature. So the reciprocal of the curvature is called the radius of curvature, and it is denoted by rho. The rho is nothing but the 1 upon d xi by ds. So the radius of curvature is nothing but the reciprocal of the curvature, and it will be this 1 upon d xi by ds. The third remark or third definition I want to say, it is a center for curvature. A point P on the normal at the point P of the curve, distance rho from it is called the center of the curvature. So what I am saying is, if you have this is the curve and there is a point P, you want to calculate what is the center for the curvature, then at the point P, you will have this is the tangent to the curve, and the perpendicular from that, that is the normal. This is the normal at the point P, and the distance rho, if this distance is rho, and then this point from this distance and this point is called the center of the curvature. So in that manner it is the definition of the center of the curvature is there. I will repeat again. A point C, so this is the point C, on the normal at the point P of the curve distance rho from it, then it is called the center of the curvature at the point. The next definition is the circle of curvature. So circle with the center C, which is the center of the curvature. So if you have this was your center of the curvature, and if you can draw a circle with this center, so if you can draw a circle here with the center, then this is called the circle of the curvature at the point P. So that is the definition of the circle of the curvature. Now, the next thing that we are going to discuss is the finding the radius of curvature in Cartesian coordinates. So again, let us recall what is the definition of the radius of curvature. Radius of curvature is nothing but the reciprocal of the curvature. Curvature is nothing but the rate of change of tangent with respect to the arc length. So here our objective is to find out what is the radius of curvature for the curve y is equal to f of xy in the R2. So if you have given this as the curve y is equal to f of xy in the R2, we have to calculate what will be the radius of curvature there. So again we are taking the previous figure, that is the, if you have this is the curve and this is the point P. At this point P, there is a tangent which makes the angle with the positive x-axis as xi. So the slope of this tangent, let us say this is the T1. So the slope of this tangent T1 will be tan xi, that we can say. And since this is the curve y is equal to f of x is given, the slope also can be calculated as dy by dx. So that is also slope of this tangent at this point P. So that means what you will have is dy by dx is nothing but the tan xi. So these two values are equal, and if I call it, this is equation 1. And dy by dx I may denote it as y1. So that's why it is, we can write y1 is equal to tan xi. So y1 square will be tan square xi. And if I add both sides 1, then it is 1 plus y1 square is tan square xi plus 1. Now again if I differentiate this with respect to x, then we will have y2, which is d square y by dx square, which is nothing but the d by dx of tan xi. Now according to the chain rule, we can say it is sec square xi into d xi by dx. And sec square I may write down as it is, and using the chain rule I can write down this quantity is d xi by ds into ds by dx, where s is the parameter length, arc length is there, length. And so therefore we can say that 1 upon d xi by ds, which is your radius of curvature, equal to sec square xi into ds by dx upon y. So sec square I can write down as 1 plus tan square xi into ds by dx, and y2 that we can write down as it is. So therefore this radius of curvature, that is 1 upon d xi by dx ds, which we have denoted as rho, that is equal to 1 plus tan square xi into ds by dx upon y2. That was we have calculated in the previously. And using the equation 1 we have here, that is tan xi is nothing but the dy by dx, so that is actually y1. That's why this is y1 square ds by dx upon y2 you will have. Now what is ds by dx? Dx by dx is nothing but the arc length, and that we can have, this is the formula, d square x is equal to dx square plus dy square, that is the length is there, so that's why dx by dx will be 1 plus dy by dx square, and so therefore ds by dx is nothing but the square root of 1 plus y1 square. So therefore this will be 1 plus y1 square into 1 plus y1 square raised to 1 by 2 upon y2. So finally we'll have the formula is 1 plus y1 square raised to 3 by 2 upon y2. That is the formula for radius of curvature for the curve y equal to f of x at any given point t. So this is the formula you will have for finding the radius of curvature. Let us solve some of the examples based on this formula. So the question is, find the radius of curvature at the point 3a by 2 for the curve x cube plus y cube is equal to 3axy. So here, according to this formula, I have to calculate what is y1 and y2. That is the concept. So derivative of the y with respect to x and y. So let us write down what is the formula for the radius of curvature. The formula is 1 plus y1 square raised to 3 by 2 upon y2. So I need to calculate what is y1, that is the derivative of y with respect to x, and y2 is the second derivative of y with respect to x. So if I call it this is equation 1, and if I differentiate this equation 1 with respect to x, we will have 3x square plus 3y square dy by dx is equal to 3x as it is dy by dx plus 3ay. So if I combine these two terms, we will have, it is dy by dx is 3y square minus 3ax is equal to 3ay minus 3x square. So therefore dy by dx is equal to 3ay minus 3x square upon 3y square minus 3ax. So this is your value of y1, I can say, and we have to calculate this y1 at this point. That's why dy by dx at this point, that is 3a by 2, if I substitute that value here, and if you simplify that, let us see what we have. It is 3a by 2 minus 3 into 9a square by 2 upon 3 into 9a square by 2 minus 3a into 3a by 2, and you can just observe that numerator and the denominator is the same, and but it is of opposite sign, so that's why the answer for this one is what? Minus 1. So the y1 is minus 1. Now to calculate the y2, we are differentiating this equation again. I call this is as 1. If I differentiate this equation 1 with respect to x, again we have the y2. Let us calculate that. Let us write down first what is the equation here. That is dy by dx into y square minus ax equal to ay minus x square. So that's why it is d square y by dx square. That is by taking the derivative of this quantity is as it is, plus dy by dx is there, and the derivative of y square is 2y into dy by dx minus a equal to a into dy by dx minus 2x. So if you want to calculate that d square y by dx square at point 3a by 2, 3a by 2, then this will be nothing but the 9a square by 4 minus a 3a by 2. This value we have calculated as minus 1, so it is minus 1 to y, that is 2 into 3a by 2 into minus 1 minus a equal to a into minus 1 minus 2 into 3a by 2. So therefore, if you simplify all this quantity, that is at point 3a by 2, 3a by 2, then we will have this is minus 32 by 3a, that is verify and check, and that is your value of y2. And you can substitute that value of y2 in the formula of radius of curvature, that is 1 plus y1 square raised to 3 by 2 upon y2. We have calculated y1 is minus 1, so it is 1 plus 1 raised to 3 by 2. And y2 we have calculated this is minus 3 by 2, 3 into a. So that is nothing but the, so we will have a into 2 raised to 3 by 2 upon minus 2 raised to 5. So finally you will have it is 3a upon 8 2 raised to 5. If I take it magnitude value of this curvature, in magnitude this will be the things. If I can say more of that, rho is this one, that is the radius of curvature, that is the rate of change of the tangent you will have. Let's have the one more example. So find the radius of curvature rho at point a comma 0 for the curve xy square minus equal to a cube minus x cube. This is the curve. So calculating the rho, we know that the formula is 1 plus y1 square raised to 3 by 2 upon y2. So for that I need to have what is the first order derivative and second order derivative. So I am differentiating this equation with respect to x, and using the product rule we have it is x as it is. The derivative of y square is 2y into dy by dx plus y square as a derivative of x is 1, then it is minus 3x square. So therefore dy by dx you will have it is minus 3x square minus y square upon 2x square. At the point a comma 0, this will tends to infinity as y is tending to 0, because the point is given a comma 0. So in that case you will not able to calculate your rho in this manner. So now what you can do, you have to calculate dx by dy and d square x by dy square. So instead of changing your equation y equal to f of x, we are trying to convert into the x is equal to g of y, and then the same formula will work for that also. So to do that, we will differentiate this equation now with respect to x. That we will do in the next page. So you can have, this is the equation. If I differentiate this with respect to y, we will have x as it is, derivative of y square is 3y plus y square as it is, derivative of x with respect to y is dx by dy minus 3x square dx by dy. So therefore this will imply dx by dy is equal to 3xy upon 3x square plus y square minus. Now you can calculate this value at point a comma 0. Then you will have 0. This value is 0. Now to calculate the second derivative. For the second derivative what we have is, this is the equation, that is 3x square plus y square dx by dy plus 3xy equal to 0. differentiating this with respect to y, what we will get is 3x square plus y square, as it is derivative of this with respect to y is d square x by dy square plus dx by dy as the derivative of this quantity with respect to y will give you 6x dx by dy plus 2y plus 3, as it is product rule is also applied here, so that is y dx by dy plus 3x derivative of y with respect to y, it is 1 equal to 0 on the other side. Now if you want to calculate, that is at the point a comma 0, that means this will give you 3a square into dx d square x upon dy square at point a comma 0 plus dx by dy we have already calculated as 0. So this term goes to 0 because 0 into anything will be 0. This term is also goes to 0. So left is 3x, this is 3a equal to 0. So finally we have this square y by dx square, that is the second derivative of y with respect to y at the point a comma 0. We will have it as minus 3a upon 3a square. So that's why it is minus of 1 upon a. So according to that, we have the rho, which is the radius of curvature, will be 1 plus x1 square raised to 3 by 2 upon x2. But x1 we have calculated is 0. That's why it is 1 plus 0 raised to 3 by 2 upon x2 is minus 1 upon a. So that's why it is minus a. If you can consider as a modulus, then it is a plus a is the radius of curvature. That completes the solution for this problem. Let us recall what we have did in this lecture. We have defined the radius of curvature. Curvature is nothing but the rate of change of tangent, or I can say how the curve is bending. So that is the meaning of the curvature. Reciprocal of the curvature is called the radius of curvature. We have also defined the center of curvature. Center of curvature is a point C is called the center of curvature. If from the point C on the normal at any given point of the curve, so we have discussed the center of curvature, circle of curvature, and lastly we have derived what is the formula for calculating the radius of curvature in the Cartesian coding, and we have solved based on that 2 examples based on that. So that's it for this video. If you like this video, please press the like button. If you have any comment, suggestion or question, please drop down in the comment box below. See you in the next video. Till then, bye bye, sayonara.